My talk is all about bias, domain and social bias in natural language processing. So let me I was supposed to say, if you have questions, if there are more clarification questions, feel free to interrupt me, and I'll try to clarify as we go along. If there are deeper questions for the purposes of the video, perhaps if you can hold off until the end so that we don't make things too choppy for the video was the request. But do hold on to those questions. So bias. What do I mean by that? And I'm going to talk about it specifically in the context of language identification, partly because it's a nice intuitive task, but partly because there's a lot more to it than you might naively think. So what is bias? If you've done any stats, you have some basic notion of what bias is. There are biases all over the place, statistical and psychologically. The particular ones I'm going to be interested in today's talk are a domain bias. So this is the idea that you train a model in one domain, you want to port it to a second domain, and in order to do that, you need to update parameters of your model in some way, and that's usually in the form of updating the priors, depending on the type of model, and the conditional probabilities for whatever features it is you have in your model. Maybe you need to update your label set, that gets harder, and maybe there are vocabulary shifts as part of that. So it's this game of updating the parameters so that you're better prepared to deal with whatever is contained in the target domain. We'll talk more about it as we go through. Related, but somewhat orthogonal to that, is the idea of dataset bias. And by that I mean what underlying properties there are in the dataset in terms of its composition. And this is, domain bias is one which is very well known in the machine learning and NLP literature, and there's all sorts of methods to deal with domain bias. Dataset bias is one that people have only really started talking about recently. And we'll talk about that variously. Model bias then is one where if you've ever done any machine learning, you've run into it. So that's the idea that your model predicts things which don't quite concord with the gold standard labels, the test labels. It's off in different ways. And you'll probably get an immediate sense of this is going to be impacted on, of course, by both the domain and the data set bias. As we move across domains of increasing separation, the model bias is going to get worse, and data set bias is going to directly impact on our model bias. And then a bias that we don't talk about so much, but is equally important, if not more important, is social bias. So this idea that there are particular social or socio-demographic groups of people that our models are biased towards or against in different ways. So let me go through each of those in turn and just say a little bit more, as well as giving you a better sense of why it is I'm going on about bias. So domain bias. I have in this slide the Penn tree bank effect. So the NLPers will perhaps understand that the Penn tree bank is it's an absolute foundational data set in NLP for parsing, for constituency parsing, which has been the absolute cornerstone of parsing research for the last 30 years or so. What do I mean by the Penn tree bank effect? That's the idea that we do our in-domain training over this particular data set, and we sort of produce ever-increasing whatever scores, unlabeled attachment scores, say, in terms of F-scores and whatnot, and we sort of see those numbers creeping up over time, and we convince ourselves that we are getting better at parsing. Problem is, we then go and apply our parsing models over something which it's the Penn tree bank in terms of what the parsing community uses out of it is Wall Street Journal text from the early 80s. So it's newswire text from a particular point in time. So unsurprisingly, if you take your tree bank from the 80s trained parser and you apply it to something like Twitter, it absolutely falls in a heap. But we can very easily lull ourselves into a sense of achievement by looking at those numbers and by tracking them over time. Okay? we want to be more realistic, I guess, in our evaluations is what domain bias is all about. And so I mentioned domain adaptation briefly and what that is. And the, I guess, canonical setting that people talk about domain adaptation in is you know explicitly what your target domain is. You've often got some small set of labeled data there, and so you're doing some supervised updates of your model parameters so that you can deal with whatever unseen data in that domain. So you know exactly what's in store through some snippet of that domain that you're moving to. And we'll talk about, in the context of language identification, lots of scenarios where that's not the case, where I can throw random things at my system and I want it to work. I don't want it to just fall in a heap. Right, so then dataset bias. So why do we care about dataset bias? Well, because we want to be able to believe that the numbers that we're generating are truly representative of whatever task it is that dataset is meant to represent. And if there are intended or otherwise biases in our dataset, then whatever task it is, we're not capturing. And I guess implicit in this is the classic ID assumption that we're making in doing any statistical modelling, that whatever our training data is truly representative of data in the wild, at least for that, data sampled in a similar way at least, not in the wild, but sampled from the same distribution. And there are examples that people have identified recently where that just really isn't the case. So these are a couple of references from the vision community, where it was pointed out that if you took some of the standard data sets from computer vision and you sat people down who were familiar with these data sets, who were on a daily basis training models over these data sets, and you said, here are 3 images, which data set do you think they came from? People were surprisingly capable of saying, oh, I know which data set they came from, even if they'd never seen those specific images before. And if you trained models up, just simple supervised models up, they could similarly do a depressingly good job of identifying what data sets these came from. And in some instances, okay, maybe they were very specific data sets with very specific object types in them. But in other cases, these were supposed to be representative data sets. And if you can identify at the data set level where something has come from, then obviously something is not quite right. So alarm bells here. And more recently in NLP, this is a paper from all of 2 days ago at EM-NLP, which was in Copenhagen very recently, in fact based off some of the vision data sets. So this is in particular in the context of data sets like MS COCO, where you've got object metadata, what objects are contained within this particular image. There are all sorts of social biases, and the particular social dimension that they were looking at in this paper was gender bias. So if you have a cooking scene, you are much more likely to have a female doing the cooking. If you have a repairing scene, you are much more likely to have a male doing the repairing. And okay, that's the reality of the data, but knowing that and knowing what impact that has on the models is very important, in particular because they observed in that paper the models pick up on these biases, and not only do they pick up on them, they amplify them. So that if you show a model one of these cooking scenes, perhaps the underlying distribution in terms of gender balance is 70-something% female, the models will learn to predict with much higher probability, 90% of cases, that it is a female. And it makes sense in terms of uncertainty and priors. If in doubt, say it's female because that's the majority class. But it's sort of going to an absolute extreme. And if we're training up models and we're letting them loose in the wild over true distributions of individuals, and they're being biased in these social ways, that is a bad thing. And if they trained up models on the Penn Tree Bank, which is data from the 80s written by largely white, male, 40-something-year-old journalists, because unfortunately that's the practicality of the Wall Street Journal at that time, what you observe in terms of the input data is it does very well over data from white, male, 40-something-year-olds. It does less well over data authored by females. It does less well also by younger authors. So age effects, unsurprisingly, creep into the data. How you write and how your grandparents write are very different things. The model is biased. The model picks up on these things. So our models are very sensitized to the sorts of data that they're trained over. And we're observing this across the board now, I guess, as more and more AI gets in the hands of the populace to somewhat caricature. If our speech recognition systems are doing very well over white, male, 30-something-year-old Californians, but not well for anyone else, then we've got an issue. There's also a legal side to it, though. So as more NLP and machine learning gets out there, it's being applied more and more in legal contexts, by governments, by public organisations of different types. And in doing so, AI models have to adhere to laws, to anti-discrimination laws. And if we can't prove so, and they have to be demonstrably adherent to these laws. It's not just that they should accidentally be adherent, they have to stand up under audit. And there's important EU legislation coming in soon, such that models can be audited to defend any prediction they're making. So that is part of this. So there's a very high bar that we need to be able to meet in terms of deploying our machine learning or NLP models in these sorts of contexts in being able to actually satisfy this criterion. It's a far from trivial criterion. So it's not just we want to be good people, it's if we want to do some of the things that people are talking about doing with AI, we have to get this right. Okay, and the machine learning community has been picking up on this, as well as the NLP community. I highly recommend this particular paper, and there'll be references at the end, and I'll make the slides available. But it's a paper from NIPS last year, the big machine learning conference. And it sort of talks through how you can do this, how we can produce models which are socially equitable or which are legally adherent in terms of not being discriminatory. And the obvious sort of things in terms of, well, if we mask out the gender features, say, for a certain task in terms of the user metadata, so fairness through unawareness, what tends to happen is the model will pick up on correlated features and basically learn gender. So that does not work, and we're kidding ourselves if we believe it does. Similarly, if you constrain your model so that it's producing similar label balance over different subpopulations between different racial groups, say, what tends to happen is the models will sacrifice accuracy. They're constrained to produce a certain number of positive and negative predictions, say, so they will just artificially produce them, and the actual accuracies you get for different racial groups can be very different. So the sort of obvious approaches really don't solve the problem. Okay, so a bit of thunder and lightning to start out with, a scene setting. On a lighter topic then, the case study I'm going to use for this is language identification. And it's a task which you've met whether you know it or not. When you fire up something like the Chrome browser and it comes up with the, do you want to translate this into, I guess, Ukrainian? It's doing language identification over the page, it's determining that it's not in one of the languages in your user settings, using something called the compact language detector. So there's a very compact inbuilt language ID model within your browser. And the basic task is it's taking a slab of text, or it's taking the first n bytes from a slab of text, and it's trying to predict what the language is. And it's a vexed thing to present flags associated with languages. I know, forgive me that. But the basic idea is for a slab of text, what language is it? So you might sort of think, well, that's pretty trivial, surely. And as a bit of an audience exercise, if I were to present you with this particular piece of text, some of you will almost certainly tell me it is Swedish. Okay, and why do we know it's Swedish? Because, yeah, we've got particular diacritics and a particular distribution of diacritics. It looks very much Swedish, and if you speak Swedish, then, well, of course it's Swedish, I can read it. Silly question sort of thing, right? So, yeah, for something like that, great, no problem. Let me give you a different example. I'll give you a moment to browse through that. Obviously, it's English. It's French, well, exactly. Is it French? Is it English? We've got bits of Latin floating around there. So, you know, it's a particular genre of text. It's, you know, perhaps a slightly uppity bit of text in that it's being very francophone. So we've got lots of French expressions sprinkled through the English text. And it's very much English. The syntax is absolutely English. You know, all of those French expressions are part of, you know, a certain idiolect, at least, of English. But, you know, understandable by someone with a certain education level, at least. But, you know, you can see how text like this would cause problems for the model, at least. Superficially, we've got a lot going on there which isn't just English. What about this one? There would be a prize for getting this one right. It's actually an extinct language. So this is an Australian Aboriginal language, one by great, they say. So, I mean, how would you pick up on this? Well, you have to know something about consonant patterns and, you know, some basic morphology of Australian Aboriginal languages to get a sense that it's probably from, you know, northern Australia somewhere. But, so, you know, there are lots of languages, is my point. There are many that we know, but there are many, many, many more that we don't know. So, yeah, it's a very large arity in terms of number of classes, classification task in practice. And we don't necessarily know about every language. You know, if we trained up a model 10 years ago based on every documented language at the time and we read it over the web now, we'd get bits of conlangs like Dothraki and whatever. And, you know, the model would predict them to be whatever, who knows, Maltese or something, and we get it wrong. So, yeah, it's hard to document all of the known languages and actually get data for them. And, you know, there are some bits and pieces of other languages and varieties of languages which are always evolving. And of course, in practice, what our models are doing is not even that, it's this. So what's the language of that document? It's binary, yeah. If we were to decode it into text, what would it be? Well, the point is, this is what our models are doing. It just sees the bit stream, or, you know, the byte stream, I guess. More sensibly, for the UTF-8 geeks, they can perhaps identify the particular pattern suggesting that it's 3 code points. And if it's UTF-8 and 3 code points, it's probably CJK. So, you know, toss a 3-sided coin, ends up this is Japanese. Okay, I think this is the task that our Lang ID models are doing in practice, right? And there's the extra confound. You know, much of the world nowadays is UTF-8, which makes life easier, but there's lots of legacy data in all sorts of weird and wonderful encodings. So, yeah, even assuming we know what the code points are, we can't do it in practice. We want our models to be able to deal with any sort of encoding. Okay, so let's start out naively, forget about all these bias remarks that I've made and just see what happens. So we're going to start building models for language identification, and we're going to make some assumptions just to make it a more tractable task. You know, how you know, they're going to be harmless things, we hope. So we're going to assume first that everything comes from a homogeneous source. You know, surely that's not such a bad assumption to make. Everything is monolingual. For any given document, there is one and only one language that it contains, and languages are homogeneous. Okay, so it's a homogeneous source as well as, you know, English is English. There are no different Englishes. There is just English. You know, it is a perfect thing, which I'm sure Grammarly produces, but is not the practicality of it. Okay, so it's just a classification problem. Okay, so we're just saying, okay, we're generating a single label for our single document relative to our training data. Okay, and I'll sort of talk about some deep learning approaches later on. For the time being, just to get us going, we're just going to play around with a very simple multinomial naive Bayes. So if you know naive Bayes, It's just the prior multiplied by the product of the conditional probabilities for each of our features. And all we're doing in addition to that is exponentiating by the term frequencies and then dividing by the factorial of the document length. Okay. So, and we're going to do that over byte n-grams. Bytes, because we don't want to make any assumptions about encodings. It's basically just a text classification task. There are all sorts of methods for text classification, of course. We happen to be using multinomial naive Bayes. And the only real difference is instead of using a bag of words, we're using a bag of byte sequences, so byte n-grams. And all I mean by byte n-grams is, and here I'm simplifying things slightly, and I'm assuming a single character is a single byte. So in practice it's a byte rather than a character there, but we're going to have 1 grams or unigrams and 2 grams or bigrams, etc. So we're just sort of chopping it up based on a sliding window of length, whatever the prefix is there, and producing all of those n-grams across our document. Okay, so then we're going to train up models across 4 different domains. JRC Aquis is a bunch of EU legalese documents across 22 languages. Debian is a lot of localized man pages and doc strings from the Debian project, Debian distribution of Linux. So we've got more languages there. So lots of sort of technical prose, very different to JRC Aquis. RCV2 is multilingual Reuters Newswire, similar sort of time period to our old friend the Pentry Bank, slightly later, but fairly similar. So it covers 13 languages, and then a bunch of Wikipedia articles from 68 languages. Okay, and so we're going to sort of have roughly the same sized data sets. We're going to do our splits, so we'll cross-validate, and we'll have 80% of the data we'll use as training, etc. Document lengths, some nice, healthily long documents, with the exception of RCV2, where they're not short, they're still thousands of bytes long on average, but the longest ones we're going to get are from Debian, from the dump of doc strings for a particular package. Okay, so if we just do the obvious thing, we train up our model in domain, we test in domain. For each of those 4 different corpora, things look good. We're at sort of mid to high 90s. JRC Aquis, we're 99%. Why am I going on about this? Solve task. Can we just get on with life? There's actually a paper which advocates language identification is a great teaching tool for undergraduate students because it's a solved task. It's a rare instance of an NLP or an AI problem where you can build a simple classifier and it works perfectly. So our undergraduate students get a bit of gratification from actually building a system which works. The only problem being, of course, is if you go cross-domain, everything falls apart. Okay, so here's where our domain bias starts creeping in. So if we're instead saying, let's train up models from the n-1 data sets and apply them to our nth domain, then things look much less rosy. So for RCV2, we haven't quite halved our accuracy, but we're not far off it. So we've sort of fallen off a cliff in terms of our accuracy if we're assuming we don't have any access to label data for our particular domain. So despite the fact we've got more training data, we don't have any of the relevant training data for that particular domain. So we've got a problem, obviously, and this is the first issue we're going to try to address. And what is the problem? It's what you call negative transfer. This idea that, well, the assumption we'd been making in our first experiment was, I know what an elephant looks like and I know what a rhino looks like. And I'm making my IID assumption, so my test elephants and my test rhinos are going to look just like what I observed in my training data. What's happening in practice, though, as we go cross-domain, is they're still elephants and rhinos, they're just very different elephants and rhinos. We don't know how to recognise them anymore. Our model hasn't had any explicit domain adaptation. And inductive transfer learning is the setting where you allow it access to label data in your target domain to be able to do its parameter tuning. We're running it in, there are a couple of different ways in which people talk about transductive transfer learning, but in the sense that it doesn't have access to any labeled data. In fact, it's a stronger version. Again, it doesn't have access to any of the data, so it's not allowed to do any even semi-supervised learning over that. We're just running it and hoping for the best. Okay, so great if we're in domain, considerably less so if we cross domain. So okay, how can we deal with this? So let's focus on the domain bias in the first instance. So the underlying problem is the models are learning great language-specific features, but some of those are domain-specific as well as being language-specific. Some of them are just language-specific. So what we really want is the high language association, low domain association languages. They are predictive of the language, not the domain and or the language. The sort of thing that you get in these data sets in practice is it's actually a different data set which comes up a little bit later, something called Eurogov. The German documents in Eurogov happen to contain lots of numbers. The Germans love talking about numbers in this particular data set. So whenever the model sees lots of numbers, it says, aha, German. Just because it's got lots of numbers, it's got nothing to do with the language in practice. Yeah, that's the sort of thing we're talking about here. Okay, so we're going to go with a very simple model here. We're just going to look at information gain as a way of trying to learn this statistical association. And if we do a plot of the per language information gain versus the per domain information gain, so all we're doing is saying what's the entropy, and we're going to subtract from that the mean information we have when we do the partitioning based on language or domain respectively. And we have a big scatter plot. I'm not sure how visible that is, maybe a little bit faint, but what we have basically is a big diagonal of features where there's a strong information gain for both language and domain, and these are the ones which hurt us when we go cross-domain. And then there's also a line, there are lots of other bits and pieces as well, but there's a strong horizontal line. And so they're the ones which we want. They're the ones which are not correlated with domain, but they are strongly correlated with language. So we want to identify those. Okay, so how can we do that? One way to do it is just to say, well, for each feature, let's just calculate the information gain across all of our languages and subtract from that the information gain for all of our domains. So that if we're up here, it's going to be downweighted considerably. If we're down here, there's not a lot to subtract off, so it's going to be high in the ranking. So that's one way that we could do it. Another way we could do it would be to say, one problem with that is we're potentially going to get lots of features associated with the dominant languages and not many associated with the minority languages, the less well-represented languages in these particular collections. So let's instead do a binarized one versus all. So, is it French or is it not French, rather than is it French or German or English or Wambaya or Japanese, which is this version. So we're conditioning on the language, and we'll subtract the domain information gain from that. Okay, and then we'll take the top end per language. There may be some overlap in those, probably not a lot though, and that's going to be the basis of our feature selection. So this is sort of, I guess, pre-deep learning, old school explicit feature selection that we're doing here. And yes, I can sort of think of all sorts of ways that we could do this via regularization in a deep learning framework. This is work which is ancient now. In 2011 this was done. I would do it slightly differently now, and the results would be slightly better, and it would take me 1,000 times longer to train my models. Right? So all well and good. The only problem is if we're trying to calculate information gain for higher orders of n-grams, so for 9 grams, say, if we know anything about combinatorics, that's going to be a very large set that I need to do exhaustive calculation of, and then the ranking of. Even the sorting is not going to be a cheap thing at that order. So we want to have some way of being able to tractably do these calculations. Basically, we have to do logging, which is expensive, and some big sums, well, not big sums, but lots of summing and logging and dividing. Can we identify some subset of those features to do the calculation over, which is going to considerably reduce the search space without costing us? There's a nice effect, another scatter plot, which again may not be super visible up the back. What we're plotting now is on the x-axis our domain frequency, on our y-axis our lang domain score, the binarized version of that. And what we observe is if we have a low document frequency, so by document frequency I just mean what number of distinct documents does it occur in. I don't care how many times it occurs per document, it's an existence-based thing. So if it occurs in very few documents, it's not going to have a high score. If it occurs in lots of documents, it may or may not. So we've got this fan-out effect, basically. So I need to test if it's got a high DF to see whether it is actually up here where I want it to be. But if it's got a low document frequency, which is a lot of our terms because of the long tail effect, I can just ignore them. They're not going to be high information gain difference. And domain frequency is very quick to calculate. You know, I can map reduce it, I can do whatever, because I'm just counting up across lots of documents. So that's a very trivial calculation, much, much cheaper than doing a big information gain calculation. So I'm going to do that. So I'm going to identify the per n-gram order, perhaps, the top n features with the highest DF, domain frequency value, and I'll do the calculation of my information gain difference there. And I'll throw everything else out. I'll just combine across my different n-gram orders, and that's going to give me my features. So, okay, good. And this is all based on byte-based tokenization, as we had before, with our venerable multinomial naive Bayes learner. And in practice, we do this over 1 to 9 grams, although in practice, we get very little once we go beyond 4 grams. So the deployed version of this system only actually goes, it's 1 to 4 grams all combined together. Okay, and then we sort of have some results over some new domains, which I don't have here. What I do have here is if we do this trick, so we have our original in-domain numbers in the green there, and then we have in the red, the rightmost column for each of our 4 basic data sets, we have our binarized version of this information gain difference. And what we're observing is for our data sets, we're either getting exactly the same as if we just did in domain, which is good. In some instances, we actually do better if we do it this way, because we're not overfitting to the training data. If we do get a drop, it's 1 or 2 percentage points. We can probably live with that. So we've both largely maintained our in-domain results and got much better cross-domain results. So this is over then some different data sets again, so a different set of Wikipedia documents and 2 others, one with a mixture of different encodings to really test that side of things. And what we're asking here is, so if I know for a particular data set for Eurogov, say that it has, I can't remember the exact number off the top of my head, it's 8 or 10, or it's a small number of languages. If I constrain my model to say anything outside those just throw out, because I produce a probability distribution, so I can just renormalize, or just throw out and max in practice. Do I do better than if I just run the model as is? So if I prune out these, or if I retrain my model throwing out these extra languages versus just having an off-the-shelf system with languages which I know actually aren't represented in my data set, what do I do? So what I have on my y-axis is if I just train over everything, over the union of all of those languages, which is 97, versus if I just retrain over the languages which exactly coincide, so using the same cross-domain trick, which exactly coincide to what's actually in that data set. I never have any extraneous languages. So the diagonal, the x equals y line, would mean there's no difference. If I'm above that, it means I'm actually doing better, despite the fact that these languages don't occur in my data set. If I'm below it, I'm doing worse. And what we observe is things are either on the diagonal or we do have some instances, so this is per document for each of these data sets. We do sometimes have things which fall below the line, but we have actually more data points which are above the line. So we actually do better in having these extra languages because we get more granularity in our training. It gives us more discrimination. So, what the conclusion from that is the more languages, the merrier. You don't suffer in having more languages. The training actually works better. And if we had a discriminative model, it would work better again, rather than a generative model. So, yeah, this feature selection method seems to work well in terms of our primary consideration of getting our cross-domain effects working. The more languages, the merrier. And there's a reference implementation of this called langid.py. There's also a C version if people want something which works crazily fast, which uses exactly the same models, it's just implemented in C. So, okay, good. That's dealing with the domain bias. Let me talk quickly about one of the other assumptions we make in terms of multilingual bias. So we're making assumptions that every document has a single language. And I'll go over this somewhat quickly so that I have time to talk about social bias. So what I mean, multilingual bias is the reality that a lot of documents out there actually contain multiple languages. Whether we believe with our English example that's the case with just those bits of French, or whether we're after something which is coarser grained than that, I guess is something we could debate. But the basic assumption is we've got a document which has chunks in different languages, and there are all sorts of scenarios where this occurs, whether it's code switching or parallel documents. A legal document, say in the local language and in a lingua franca, or sort of boilerplate. You've got a website which has boilerplate in English, say, and then the local language has content, whatever it is. Okay, so there are all sorts of reasons why we might want to do this. And the setting we're going to look at this in is to say, what are the relative proportions of the different languages? So the monolingual version of this is going to be, well, it's 100% whatever, modern standard Arabic, say, but the model also should have the facility to say, well, it's 80% modern standard Arabic and 20% Egyptian Arabic or whatever, depending on what the mix of languages we've got access to, or language varieties we have access to is. And the way we're going to approach this is using a generative mixture model. All I mean by that is we're going to have some latent representation which we're mapping our documents to, which in our case it is going to be our languages. So, for something like a topic model, something like latent Dirichlet allocation, say those are going to be latent. There is no explicit representation of them. We want to learn them from the data. In our case, we're going to assume that we don't know what the languages are for a particular document, and we're trying to learn that mixture of languages, so they're latent in that sense. Okay, so if you've seen LDA before, the basic setting here is we've got a document, we've got the words that are contained within that document. We're assuming that each of those words is generated based on some generative process. We have a larger generative process that's generating the documents in our document collection, and a prior associated with that. And similarly that we have our topics, which are also affecting the generation of the individual words. So this is our latent structure up here. Okay, if that doesn't make sense, don't worry too much, you don't really need it to understand what's going on. But for those who have run into LDA before, the basic difference here is simply that our topics are our languages, words are our byte sequences once again. In terms of the individual languages, which we're saying are latent representations up here, we can actually get monolingual data to do the direct estimation of the conditional probabilities associated with those, so we can estimate that directly. The thing that we don't know is for a given document, what tokens are taken from what language. So we want the model to learn that directly, so we use a Gibbs sampler to do that. And I'm not going to go into the details of how that works here. So then we've got this generative process which says, well, if you give me a set of languages, I can give you a distribution. I can give you allocations for individual words, which will define a probability distribution. The question then is, well, but what are the languages? We need to have some process for identifying those. And if we do this over the full power set of different languages, for any reasonable set of languages, that's going to be very expensive. So what we do instead is a greedy approach, where we say in the first instance, okay, let's try to identify what are the languages where there is likely some representation within this document. So we just rank our languages independent, and we'll take the top n out of those, conditioned on the document length. And then we'll work through each of those. So we'll sort of say, okay, let's start out and assume this document has been generated from no languages. Is that a better fit than if we assumed it's based on our top ranked language? And in every instance, the answer is going to be yes. And then we say, okay, so let's lock in, because it's a greedy algorithm, that top language. Now let's ask the question, if we take our top two languages, Swedish and Macedonian here, is that a better model of our document? And we're assuming there's some threshold that we need to meet in terms of our difference in the relative likelihoods we're getting out from our model. If so, we'll say, okay, lock in Macedonian. Now let's try, what are we up to, Bulgarian? The answer is, well, no, Bulgarian, you're better off with just the top two. But if we add Danish, yes, we get better fit. So the answer is going to be, well, it's those three languages and the topic distribution that defines. So that's where we get our probability distribution from. I realise I'm rushing through the details a little bit. I'm happy to answer questions about this at the end. Let me skip over a lot of the details here. Suffice to say that it works. So yeah, this is comparison to other methods, and it does reasonably well based on a synthesized data set of sort of different mixes of 1 to 5 languages and precision recall F-score in terms of the token counts or the byte counts in the respective languages. Okay, so this is an extension of the original lang_id.py, it's something called polyglot, to sort of do this language mixture distribution, so that we've relaxed our assumption about all documents being monolingual. Okay, so then into the social bias side of things, having got you hopefully worked up about that, or at least convinced that that's an interesting thing that we should be looking at the start of the talk. So, yeah, okay, all good. Things seem to be rosy. We do well cross-domain for these different document collections. What could go wrong, or what am I not telling you? Well, there was a wonderful paper at ACL a little earlier this year, a month or so ago, who asked the question, well, so you're assuming that languages are homogeneous in the work that we've done and a couple of other people had done, and everything looks rosy in that context, but we know that languages aren't homogeneous. You've got lots of different varieties of languages, be it English, where you've got lots and lots and lots of global varieties, or Arabic or Spanish or Ukrainian, you've got lots of different dialectal variations within the country. So languages are not, you'd be doing well to find a language other than a constructed language which is internally consistent. You're always going to get gradations of it, whether that's over age or over time or geographically. So let's actually try to measure how well the different lang_id systems are doing over diverse test sets. And we're going to construct that it's all based on Twitter data in the geographic diversity case. In the multilingual diversity set, it's synthesized, but sort of Twitter length. So we also have the confound that these are much shorter documents than a lot of what we've been seeing to date. And I can tell you separately about Twitter lang_id independent of this. But the basic heuristic that we're going to use to generate these data sets is to say, well, we're going to do an ensemble approach across different language identifiers, where if we can find users who are over some reasonable volume of tweets, the lang_id systems are happy that it's always the same language. We'll assume they're monolingual, and so we'll automatically label them based on that language, and then see how well, when we start doing the tweet level prediction, models are really doing. Okay, so in constructing the data set, we have this redundancy in terms of number of tweets and predictions over the individual ones that helps our models. When we're doing it in the wild, we don't have that luxury. So And we're going to do similar tricks for generating, so some of these are also going to be the basis for generating training data sets, which we explicitly train on. We're also going to add a lot more diverse data sets from the 4 that I talked about earlier. Data sets from African American vernacular English, for example, or urban dictionary, or all sorts of bits and pieces, in terms of more social English data. So this is largely focused on English, but they're doing this across 70 languages, I think it was in total. And I should say, this isn't work of mine, this is work from Stanford. And then they said, okay, well, let's build a language identifier which is hopefully going to be more socially equitable, which we're going to explicitly train by giving it exposure to all of this training data from all these different regions of the world and varieties of English through the training data. So here they used a deep learning model, that's just a character-based model. It's a sequence-to-sequence model based on 3 layers of GRUs with attention. If you're a deep learning person, that will mean something to you. If you're not, it probably won't. And they sort of train it up over chunks of all of this data, hold out some for testing. And as part of that, they make sure they balance the training data set across languages, a little bit like the trick that we had before in terms of our binarized information gain differences. We made sure we took the top N per language so that we don't have bias towards particular languages. So they're sort of doing similar things in terms of the relative amount of training data or the maximum amount of training data that they have at least per language. And we end up with a very sobering, for us, in terms of the developers of the first system here, set of results in that what we have is in the green pair of bars results over the geographic data set. So you're sort of saying, okay, so I've got a user from Nigeria, say, who's an English speaker, versus Australia versus Singapore versus wherever else, and then also for other languages. And the left bar is the micro average, so how well are we doing per tweet? So there we do well. Whereas the right bar is the macro average. So if we weight each language equally, how well do we do? So I'm not going to allow you to get away with doing well over the big languages, the English and Spanish, and Dutch is also very big on Twitter, say, and very poorly over the tail. I want everything to be balanced up. And so what we find is we do very badly at macro averaged, these are all F scores, as does the Google system. So we're better than Google, but we're still not anywhere near as good as this explicitly socially equitably trained system from Stanford. And similarly over a data set from Twitter, something called the Twitter 70 or Twitter T70, slight typo, where when we do the macro averaging, we don't do very well at all over the tail, and that really drags the results down. And perhaps even more worryingly, they then did an analysis to say, well, let's assume we're building a health monitoring system. So this is for English now, just for English. And we're going to do it based on keyword search, so a bit like a sort of flu outbreak detector, say you're sort of searching for flu and influenza maybe. And we're going to measure how well the recall of that system, so we're assuming we do our keyword search and then we port it through a language identifier and we say, okay, just give us the English tweets. What is the recall? So how much are we throwing out that we shouldn't have thrown out for our different systems? And we're going to, on the x-axis, then break that down based on an index of human development. So as much as I hate to say it, we're going to have Australia and the US up the right-hand end of there, and we're going to have places like Nigeria down the left-hand end. And very, very sobering graph. We throw out a lot of the data. We say it's not English, where EquiLD does a much better job over the Englishes from less developed countries. because it's been explicitly trained to do that. We didn't have that. We were making much simpler assumptions about our data. So we had data set bias in our training data. So what does all this mean? So I guess consistent, so I haven't told you, I guess, the second part of the story in terms of the paper from AI-NLP that I said was presented 2 days ago, where they were observing this amplifying effect. So they were then trying to train their models in such a way that you could reduce or nullify the amplification but keep the overall performance up, and show that they could do that largely. But similar to that paper, what we're observing here is if you explicitly train a model in terms of the training set and how you set up your objective function, you can train it in such a way it's less biased. So it's still biased here. We don't have a flat line there, but it is at least less biased than it was before. That's a similar story from the AI-NLP paper. But we have to know what it is we're biased against to be able to debias, I guess is the clincher here. So we're sort of making assumptions about the sort of bias we're going to observe. We're constructing our data set in such a way that we can reduce that bias. We can measure the fact that we are in fact reducing that bias. What other biases do we have? I don't know. We're probably just as bad over other things because we haven't explicitly trained our model to avoid those. And where we're at the moment, it's still very early days, I guess, in this space, is it's only if we're explicitly training our models to reduce these biases that we can show that we're reducing them. I suspect elsewhere we've got similar amplification effects going on as what others have observed. And it was a bit of an unfair comparison, I guess, not wanting to be defensive, because it was just us off the shelf. There was no retraining. It would be interesting to see what happened if we trained our simpler model over the same training data, because I suspect we would look much healthier there. And as I say, they're kind of doing it just through the data sampling. If they did more explicit regularization, I suspect they could get even better results here. So it is it's excellent work, but I think there's a lot more that can be done in this space. If anyone's working in this sort of area, I strongly encourage you to look at this sort of area. I think there's a lot of high impact work to be done. This is a big complex deep learning model. It's orders of magnitude slower, in fact, than lang_ID.py. But there's lots of interesting work that's coming out now in terms of how we can make our models more efficient. I refer you to some papers in that space. So let me conclude on that somewhat sobering note, sobering for us at least, in terms of reflecting back on where we started. So we said that domain and social bias was something that we were very interested in for very real reasons. I guess for domain bias it was more for empirical reasons. For social bias it was for legal adherence, as well as just being good global citizens and making technology equally equitable across different subpopulations of the world. Domain bias is a fairly well-known one, and there's all sorts of literature that I could point you to there. What is harder is the generalization question, trying to produce models which we can just deploy over any old data. So you can have a downloadable tool and people can deploy it. You can be reasonably confident that it will do as good as anything. Perhaps not quite as well as a complete in-domain system, but it won't just fall apart. Social bias, though, is a much less understood, much newer topic, and a more important one with lots of work still to be done. And where things are at the moment is it's very much we explicitly train away the bias. How we can get beyond that is a big question mark. So with that, let me just quickly acknowledge my wonderful collaborators who were involved in the bits of my work that I presented here, and funding agencies. And thank you for your attendance.